All right, time to review some limits as we get ready for our limit test. So let's go through this review here. So we have a function here with a rational function, and we want to find some limits. First thing we'll want to do here is we want to factor this thing. This is going to be x plus 5 times x minus 4 all over x minus plus 4 times x minus 4. Okay, so this is equivalent to x plus 5 all over x plus 4 at all places but 4. All right, so if we find the limit as x goes to 0 of f of x, well, that we can just plug in. So the limit as x goes to 0 of, and I'll go ahead and put the simplified one in here, x plus 5 over x plus 4. And so we got direct substitution. This is just 0 plus 5 over 0 plus 4, which is 5/4. All right, so direct substitution is not a problem. So let's go over here to b. So as x goes to infinity here, well, let's write this out. We can use actually either of these versions. Let me go ahead and just write the original one down, because this will be equivalent. And we know that when we go to infinity, the small terms don't matter, the small powered terms, because at infinity, infinity squared is going to be the most important. And so that is just going to be the limit as x goes to infinity of x squared over x squared, which is just 1. Because x squared over x squared is 1. What about x going to 4? Well, so the big idea is that we have a problem when we have this original 1. I'll write it in factored form. X plus 5 times x plus 4 all over, sorry, that's a minus 4 there. So x plus 4 times x minus 4. Okay, so right now, if you plug in 4, we're going to have 0 on the bottom, 0 on top. But because it's factored, we can see it. That cancels. This is equal to the limit as x goes to 4 of x plus 5 times, or over, x plus 4. And so now plugging it in is not a problem. We can do direct substitution. That's just 9 on top over 8, and we're done. Okay. All right, so we're going to graph a piecewise function here and find its limit. So first thing we're going to do is graph. So remember, when we're graphing here, we've got here a cutoff point at -1. So -1 here, that's kind of a point. I'll put a line there. That's not an asymptote, just kind of reminder that that's our cutoff. So here we have two lines. We've got the line y equals 1 minus 2x. That's a y-intercept of 1 and a slope of -2. So going down. And this is for everything that's to the left of -1. So and it's including -1. So it would be this part. That's what we want, and it's going on forever up there. And then we've got x plus 4. Well, this is kind of a bad graph setup for this. But x plus 4 would go from here, slope of 1. And we're going up there. And it's going to be an open dot here, but that dot's filled in by the other graph. So we get a V kind of thing like this. It's supposed to be a line. So there's our graph. Whoops. Okay. So we want to know what's the limit when x goes to -4. Well, when x goes to -4, we're just going to plug it into here, in this first one, because that's just the value of f of -4. So it's whatever f of -4 is, because that's not a whole there or anything. And f of -4 means we use the first one. So 1 minus 2 times -4, which is 9. And then as x approaches 2, well, that's, again, not a problem, so f of 2. And so just plug that into the second one. That's just 2 plus 4, which is 6. And the limit as x approaches -1, now the question is, well, look at that. My graph is all goofy like that. What happened to that graph? Now we got it. All right, so as x goes to -1, which was our cutoff here, there is a limit. We have a negative limit, a left-hand limit, and a right-hand limit. They're both going to the same point, and that same point is 3. So remember, the limit is looking for a y value. So when we're finding a limit, we're finding a y value. All right. Here's a good problem. This is an AP test kind of problem. So we've got a rational function, and we got some missing values. So we want to know what would make this limit go to 5. Well, the limit will go to 5 if this function at infinity is 5. So the limit as x goes to infinity of ax minus 12 all over 3x minus b. Well, no matter what these a and b are, those will go away, and all that's left is the ax and 3x. So this is equal to the limit as x goes to infinity of ax over 3x. And since those x's cancel, then we have this is equal to a over 3. And we want that equal to 5. Since we want that equal to 5, then a has to be 15. All right. That's the idea there. What about this? We want a limit as we go to 4 to not exist. So we can take that ax, we want the limit as x goes to 4 of ax minus 12 over 3x minus b. So we want the bottom to be 0 when x is 4, because that would mean that it doesn't exist. All right. So basically, we just want 3x minus b to be equal to 0 when x is 4. So 3 times 4 minus b is 0, and we can kind of see that b is going to be 12. Multiply and add b to both sides there. All right. And so if b is 12, and also a would not, well, yeah, that'd be fine. So there is an a value, I suppose, that could factor it out, but we're not worried about that. So there you have it. So now let's make a function here that we have these characteristics. We know there's a removable discontinuity at x equals -3. So that means that the factor x plus 3 is going to be able to be factored out. We want a non-removable discontinuity at x equals 2. Well, non-removable, that is an asymptote. And asymptotes happen when we have factors in the denominator that won't cancel. And so there it is. Directions say we don't need to simplify. Great. So there's our function. Yeah, that's it. All right, time for some algebraic limits here. We've got a few different types of limits. First, we have polynomial expressions here, rationals, functions with the polynomials in the numerator and denominator. And so we want to factor. The key here is factoring. Limit as x goes to 2, and x plus 2 times x minus 2 all over x, what is this, plus 6 times x minus 2. Looks good. And so the x minus 2's cancel. And so this is equivalent to the limit, yes, we need to keep this limit around, we haven't used it yet, of x plus 2 over x plus 6. Well, now 2 is not a problem. 2 was a problem here, because if you plug 2 in here, you'll get 0, and plug 2 in here, you'll get 0. But if you plug 2 in here, it's not a problem. So let's go ahead and do that. We get 2 plus 2 over 2 plus 6, which is 4 over 8, which is a half. All right. Then we have limits where we have radicals in it. When we have radicals in it, we want to multiply by the conjugate. So we're going to multiply top and bottom by the conjugate of the expression that has the radical in it. Okay, and the expression that has the radical in it is the bottom in this case. Sometimes it's the top. So we're going to multiply top and bottom by that. We're really multiplying by 1. And when we do that, let's rewrite. We're still talking about the limit. We haven't used the limit, so we've got to keep copying it down. We've got, don't try to multiply out the top, okay? Now, I kind of jumped a step here because really we should have tried our direct substitution. Let me write this down and we'll go back and try that out. When we distribute this, we want to remember that a plus b times a minus b is equal to a squared minus b squared. And so here's a minus b, here's a plus b. So when we multiply this out, we're going to get the first thing squared. 3 squared is 9 minus the second thing squared. What's the second thing? Well, it's the square root of 5 minus x. And when you square that, you get 5 minus x. The square root goes away. Those parentheses are real important. So if you make a mistake, it'll probably be with these parentheses because this negative is going to get distributed. Now back up here real quickly. In the original expression, we should have plugged in -4. Plug in -4, the top is 0. Plug in -4, the bottom becomes 0. Test that out. And so that's the first thing you should try because you may not need to do this if you can just substitute. So, all right. We now have the top x plus 4 times this. Don't try to distribute this out. Remember, 4 is the problem that we're trying to get rid of. So we're hoping that this bottom simplifies to x plus 4. And if we distribute this, we get 9 minus 5 plus x. And so that's going to be a 4 plus an x. And these are going to cancel out. And we're left with just that radical expression, which now we can substitute -4 in for x here, because this is canceled out. This is our expression that's left. Plug in -4 there, and we get 3 plus the square root of 5 minus -4, which is 3 plus the square root of 9. Square root of 9 is 3, which is 6. All right. So we've got polynomials that we factor. We've got square roots like that. And now we have some trig. And so with this trig ones, we want to use our special trig limits that we know. And so let's change it into sine and cosine. This is sine of 3x over cosine of 3x. Tangent is sine over cosine, remember that? And this is sine of 4x all over 1. We'll make it a fraction just for kicks. Now, we wish that we had some matching values here for the arguments. And the argument's this thing inside, okay, for the angle. Now, first of all, this cosine of 0 is 1. Oh, you know what? This one turns out to be pretty easy. So I think this problem was supposed to be cotangent, but You see, here's why you check direct substitution. When we do direct substitution, well, plug in 0, the sine of 0, 3 times 0, all over the cosine of 0, times the sine of 4x, or 4 times 0, all over 1. Well, the sine of 0 is 0. Cosine of 0 is 1. Sine of 4 times 0 is 0 over 1, which is 0. All right, so direct substitution works here. Now, what would be a more interesting problem is if this is cotangent, okay? And if that's cotangent, then we have a little different situation here, okay? And so let's do that real quickly. The limit as x goes to 0 of cotangent of 4x, 3x, sine of 4x. And this becomes, this situation, cosine of 3x over sine of 3x times sine of 4x. All right, and so here, now when we plug in 0, we get a problem because sine of 3x is 0. Sine of 0 is 0. So if the denominator is 0, that's a problem. So what we want to do is this. We want to change this. We want to rewrite this and sine of 3x. That's a funny looking s. And then we got the sine of 4x over 1. I'm just going to kind of rearrange some things. And then cosine of 3x. Cosine of 3x is not a problem. Now, we wish we had a 3x here because we know that limit of x over sine of x, okay? That's a 1. But if we're going to put a 3x here, we've got to put a 3x over here. All right, make that blue there so we can see we added it. Now we'd like a 4x over here. So we just multiplied the bottom by 4x, so we've got to multiply the top of all this by 4x, so we've got to put a 4x on top there. And now everything's equivalent still, but we know what this limit is. The limit of this one as x goes to 0 is 1. The limit of this factor is 1. And here when x goes to 0, oh, looks like we still have a problem, but these x's cancel. And so plugging in 0 here, cosine of 0 is 1 times the 4 that's left over there times the 3. And what are we left with? 1 times 1 times 1 times 4/3, which is 4/3. Okay, that's a better question than what was printed. And on a test, that's probably what we'll see because that's what we need to work on. All right? How about this one here? We've got a compound fraction. And so we want to multiply this whole thing by the denominator. So we want to, the problem here, what makes this really ugly is this denominator. That denominator is what we need to get rid of. Now, if there's more than one denominator, we're going to multiply by the common denominator. All right? So we want to multiply by what that is, because when we distribute that, the denominator will go away. So we distribute this. Now, these parentheses are important because we're multiplying binomials here. And we get the limit. As x goes to 3, we're going to distribute here. We get 2 times x minus 1. When we multiply this x minus 1 times this term, the denominators cancel. So we have x plus 1. These parentheses are really important. Don't forget to put this in parentheses, even though those parentheses weren't there, because this negative, which is now here, is going to affect that. And we've got x minus 3 times x plus 1 minus 1. Don't try to distribute this denominator out. Leave it alone. Okay, because we're trying to get rid of this x minus 3. That's the problem, which again, we didn't try direct substitution. We should have checked that out. But distributing this 2 here, we're going to have 2x minus x, which is x, and a negative 2 minus 1. Negative 2 minus 1 is a minus 3. So the numerator simplifies to x minus 3, which is good because that's going to cancel now. And so the whole goal of doing this was to cancel this. Now you got to leave a 1 behind. And so this simplifies to the limit as x goes to 3 of 1 over x minus 1. Now direct substitution is not a problem. So plug in that 3 there, and we have 1 over 3 minus 1, which is 1/2. All right. So a couple more little situations here, little strategies. All right, now we got some infinite limits to finish this section off. And so on this infinite limit here, since we're going to infinity, we need to cross out small terms. However, little twist here, we've got to distribute this here. You can't just go crossing things out. It's pretty tempting just to go crossing out like that 25. But you can't do that. We've got to actually go ahead and multiply this out, which shouldn't be too tough. We get an x squared. Nope, sorry, that's an x cubed. X squared times x. We get an x squared. We get a minus 25x minus 25. All right. Now, multiplying that out, all that really matters now, because when we go to infinity, is these small terms don't matter like we've already talked about, okay? But we get limit as x goes to infinity of 4x squared over x cubed, which is, that simplifies to the limit as x goes to infinity of 4 over x. And so as x gets gigantic, this is 4 over a million, 4 over a billion, 4 over a trillion. And so this is going to 0. Okay, anytime we have a larger degree on bottom than on top, the limit is going to 0. All right, and then what about this guy? Another infinite limit going to infinity here. And so at negative infinity in this case, these small things don't matter. Okay, can't cross out the square root or anything like that, but we can break it down as x goes to negative infinity. The square root of 49x to the 4th all over x squared, and that top simplifies to 7x squared over x squared. And these x squareds are going to cancel, and that's great. And that just becomes 7. All right, there you have it. There's a little bit of everything, all the different types of main limits we need to be aware of, okay? We have factoring the top and the bottom so that things cancel, multiplying by the conjugate here, and on this one over here, trying to get x, sine x over x, or vice versa, okay, or some multiple of x. Here we want to multiply by the greatest common denominator. And as we go to infinity, we cross out smaller terms once we have the polynomial, and then simplify. And then, in the end, consider the simplified version, and that gives us our limit.